Hello everyone. Today we are going to continue on digital circuit. So in the last class, we introduced De Morgan's law, which states the relationship of logic and logic OR. Right? If we have A plus B bar, according to De Morgan's law, that equals to A bar times B bar. Right? And if you have A times B together bar, that is A bar plus B bar, right? And De Morgan's law can be summarized by a single sentence, which is break the line, change the sign, right? The line we want to break is this bar, and the sign is either be summation or multiplication, right? And we also introduced decimal numbers. And binary numbers. We mentioned that decimal numbers has 10 different digits, has 10 different values or different numbers to represent a number, right? But binary numbers only use 2 digits or 2 different values to represent a number, and they are 0 or 1. We also mentioned the transformation between these two numbering systems. If you want to convert a binary number to the decimal number, the method we use is some kind of decoding method, right? For instance, if the binary number is 1011, the corresponding decimal number is 1 times 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. And those power numbers are positions of each digit, right? And the method we count the positions is from right to left and starting from 0, right? So in terms of this example, positions of digits are 0, 1, 2, 3, right? So correspondingly on these power numbers, they are 3, 2, 1, 0, right? And after you decode a binary number in this way, then you can do the calculation to find the corresponding decimal number. And for this binary number, the decimal number value is 8 plus 0 plus 2 plus 1, and that is 11, right? And we also introduced how to find the binary representation of a decimal number, which is the transformation from decimal number to binary number, right? And the method we mentioned is called repeated division by 2, right? For instance, if you have 11, this is a decimal number. If you want to find the corresponding binary representation, we just need to divide 11 by 2, right? And we mentioned that this notation, this mark, means division, and we put the number to be divided inside the division notation, and we put the division number on the left hand side, result on the bottom, and the remainder in the same row with the result, right? So here in this example, 11 divided by 2, the result is 5, and the remainder is 1. 5 divided by 2, result is 2, remainder is 1. 2 divided by 2, result is 1, remainder is 0. 1 divided by 2, result is 0, and the remainder is 1, right? And we said the binary number, or the binary representation of the decimal number, is lying in remainders, and the order of this binary number is from bottom to top. So the binary representation of decimal 11 is 1011. Right, so this is the method how we change or how we convert binary number to decimal numbers, and how we convert it back, right? At the beginning of today's class, I want to show you I want to show you one more example of converting decimal number to binary number. Give you another example like this. Example 2. Here let's consider a more complex situation. Let's say if we have a 3 digits decimal number, 294, okay, 294. This is a decimal number, and we want to find what's the binary representation. The method is the same as we introduced before. We can also use repeatedly division by 2 method. So we can divide 294 by 2, and that is 147. Remainder is 0. And 147 divided by 2, the result is 73. Remainder is 1. And 73 divided by 2, remainder is 36. Result is 36. Remainder is 1. And continue division by 2, that's 18. Result is 0. 18 divided by 2, result is 9. Remainder is 0. 9 divided by 2, result is 4. Remainder is 1. 4 divided by 2, result is 2. Remainder is 0. 2 divided by 2, that's 1. 0. And 1 divided by 2, 0 and 1, right? So the binary representation of 294 is 100. 100. Okay. Okay. By the way, when we should stop divide the result by 2? When you have 0 in the result, then we stop, right? Because 0 divided by 2, the result is always 0, and the remainder is always 0, right? So there's no meaning to continue divide 0 by 2. You just add more zeros in front of a number, and that is meaningless, right? All right. Today, a new concept we're gonna introduce is called binary fraction. We all know decimal fractions, right? For instance, if we have 5.2, we all know this is a decimal number, and that is a decimal fraction number. And we can decode this decimal fraction number. This 5 actually is representing 5 times 10 to the power 0, right? And 2 behind the decimal point, actually that represents 2 times 10 to the power minus 1, right? So here we can write this decimal number as 5 times 1 plus 2 times 0.1. And you see these power positions are also following these power values are also following the position of the digit, right? Uh, but here, since we have decimal points, we have two parts. The first part is numbers or digits on the left hand side of the decimal point. So the way we count the positions is the same as we mentioned. We're starting from right to left and starting from 0. We only have one digit on the left hand side of the decimal point. So the position of 5 is 0, right? And the right hand side of the decimal point is the other part of this number. To count these positions, you're starting from right to left and starting from -1, right? So here 2.2 is the only digit on the right hand side of the decimal point. So the position of digit 2 is -1, right? I'll give you another example. For instance, if we have 1, 2, 3, 4 times 0.56, this is a decimal number, right? The left hand side of the decimal point, we have 4 digits, and the position of these 4 digits are 0, 1, 2, 3. To the right hand side of the decimal point, we have 2 digits. Positions of these 2 digits are -1 and -2. Alright, so we can write the decoding formula or the decoding structure of this decimal number. That is 1 times 10 to the power 3 plus 2 times 10 to the power 2 plus 3 times 10 to the power 1 plus 4 times 10 to the power 0 plus. So this is the left side of the decimal point. We also have the right side of the decimal point, and they are 5 times 10 to the power -1 plus 6 times 10 to the power -2. Right. And you sum them together, that is 1000 plus 2 times 100 plus 3 times 10 plus 4 times 1 plus 5 times 0.1 plus 6 times 0.01. Right. For binary numbers, we also have similar structures. For instance, if we have 101.01, okay, this is a binary fraction number, and we can also decode this binary fraction number in the same way we decode a decimal number. For the left hand side of the decimal point, we use the same method as we introduced before to count positions. We also starting from the right to the left and starting from 0. So positions of digits on the left hand side of the decimal point are 0, 1, 2. And for the right hand side of the decimal point, digits are -1 and -2. Positions are -1 and -2. Or after we figure out this point, we can decode this binary number. The first digit, the first one is 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0, right? So the first digits are 101 are decoded. For the right hand side of the decimal point, they are 0 times 2 to the power of -1 plus 1 times 2 to the power of -2, right? And then you can find the decimal representation of this binary number, and it is 1 times 4 plus 0 plus 1 times 1 plus 0 plus 1 times 0.25, right? 2 to the power of -2, that is 1/4, which is 0.25. Right, so now we can sum them together. That equals to 4 plus 1 plus 0.25, which is 5.25. Okay. So that's the decimal representation of this binary fraction number. Okay. Alright. So now some people may ask, how about can we convert a binary fraction number back to the decimal fraction number, right? Can we do this job? Binary fraction to decimal fraction. The answer is yes, and the method is pretty similar. I'm sorry, the reverse way. Yeah, put this to the left hand side and put this to the right hand side. Right. Can we convert a decimal fraction number to the binary fraction number? The answer is yes. And the method we use is called successive multiplication by 2. Okay. Successive multiplication by 2 method. So the main idea of doing that is we just need to repeatedly multiply a fraction decimal number by 2 and record the integer numbers. Let me show you how to do that. For instance, if we have 0.1825, this decimal fraction number, and we want to find what's the binary representation, right? We just need to continually or successively multiply 0.8125 by 2. So the first time of the multiplication, that equals to 1.625, right? And here we record the integer part, right? We write it here, that is 1. And then we put the fraction part to here and multiply the fraction part by 2 again, right? So here, that is why we call this method as successive multiplication by 2, because here we do the multiplication by 2 again. 0.625 times 2, that equals to 1.25. And again, we repeat this operation. We record the integer part, that is 1. And then we put the fraction part, 0.25, to here, and do the multiplication again, right? 0.25 times 2, that's 0.2, that's 0.5. The integer part is 0, and the fraction part is 0.5, right? 0.5 times 2, that equals to 1.0. And here we have 0 in the fraction part, then we stop. But we still need to record what's the integer number, that is 1, right? Why we need to stop when we have 0 in fraction part? Because as you can see, 0 times 2 is always 0, right? So it is not, it is meaningless for continuing multiply 0 by 2, right? So here we get a bunch of integer values. The binary representation of this fraction number is lying in these integers. The way we find the binary number, or the order of this binary number, is from top to bottom. Okay, it's the opposite direction. It's the opposite order that we use in repeatedly division by 2 method. This one, the order of binary numbers for this method, repeatedly division by 2, is from bottom to top, but here is from top to bottom, right? So we have 1101, 0.1101. That is the binary representation of 0.8125. Okay. Alright, then some people may ask, what about if I have a number, for instance? What about if I have number 12.75 and I want to find what is the binary representation of this number? So this fraction number contains both integer part and the fraction part. So for the integer part, to find the binary representation, you use repeated division by 2. And for the fraction part, you use successive multiplication by 2. Okay, let me show you how to do that. So first, for the integer part, that is 12, right? So 12 divided by 2 is 6, remainder is 0. 6 divided by 2, result is 3, remainder is 0. 3 divided by 2, result is 1, remainder is 1. And 1 divided by 2, result is 0, remainder is 1, right? So 12 as a single decimal number, single decimal digit integer number, that is from bottom to top, right? 1100. That's the binary representation of 12. And then for the second part, which is the fraction number, that is 0.75, do the successive multiplication by 2 times 2, that equals to 1.5. Here, keep the integer part, which is 1, and put the fraction part times 2 again, multiply by 2 again. That is 1.0, right? Integer part is 1. So 0.75 is equivalent to, from top to bottom here, it equals to 0.11 as a binary fraction number. And after we finish these two parts, we can combine them together to find the final result. So 1.75 equals to, 12.75 as a decimal number, that is equivalent to 1100.11 as a binary number, right? Alright, so that's how we handle the binary fraction numbers. Okay. Alright, another thing I want to introduce in this class is called signed binary numbers, which means negative and positive binary numbers. Here I want to introduce a concept which is called signed numbers. Okay. For instance, we have two types of numbers in decimal numbering systems, right? Negative numbers and positive numbers. For instance, -2 or -2 is a negative number. +2 is a positive number. The same configuration can be applied on binary numbering systems either. For instance, we have positive binary numbers and negative binary numbers. Let me introduce how to represent positive binary numbers first. To represent a positive binary number, the method is very simple. For instance, if I want to represent +12, this decimal number, in the binary representation, you just need to do the normal decimal number to binary number transformation, and then put a 0 in front of the binary number. Here 12 we already find what is the binary representation. That is 1100, right? And since this is a positive binary number, you just need to add a 0 here in front of a binary number to indicate this is a positive binary number. Okay. So the method to represent a positive binary number is add 0 in front of a unsigned binary number. Give you another example. How about positive 5? How to represent positive 5 in binary representation. So first, you find what is the unsigned binary number of 5, right? So 5. So to find the unsigned binary number of 5, you use repeatedly division by 2, right? 5 divided by 2, result is 2, remainder is 1. 2 divided by 2, result is 1, remainder is 0. 1 divided by 2, result is 0, remainder is 1. So the binary representation is 1, 0, 1. And after you find the unsigned, this is the unsigned binary number. After you find the unsigned binary number, you just need to add a 0 in front of it, and that becomes positive 5 in decimal numbers. Okay. Then how to represent a negative binary number? To find a negative binary number, the method is not as simple as add 1 in front of an unsigned binary number. It's a little bit complicated, but it's not too hard if I give you the steps to follow with. So the first step to represent a negative binary number is you find the positive binary number first. Okay, that's the first step. Second step is you flip the bits. Flip the bits means whenever you have 0 for a digit, you change that to 1. Whenever you have 1, you change that to 0. Okay. And the last step is add 1 with the flipped number. Okay, so how to do that? Let me show you. For instance, if I want to represent minus 12, negative 12, this negative decimal number in the binary representation, right? So the first step, we find the positive 12. What's the representation of positive 12? Here we already have the answer. That is 0, 1, 1, 0, 0, right? So second step, we flip the bits. Whenever we have 0, we change that to 1. Whenever we have 1, we change that to 0. So the result after flipping the bits is 1, 0, 0, 1, 1. Okay. So the third step is add 1 with the flipped number. This is the number after the flipping, right? So this is the flipped number. And here we need to sum this number with 1, and the result is minus 12 in binary representation. So here the difficult part is how to do the summation with binary numbers, right? Before I show you how to do the summation here, let me show you a simple example of how we do summation in decimal numbers. Okay, for instance, what's the result of what's the result of 4 decimal number plus 4 decimal number, right? Some people can calculate that without do any calculations, right? You can do the calculation in your mind. It's very straightforward answer. That equals to 8. But when you do the calculation, you actually follow this way. You sum these two 4s together, and the result is 4 plus 4, that is 8. Right? Very simple. How about 2 decimal number plus 8 decimal number? What's the result for that? So you can also do that. That equals to 10. Very simple. But when you do the summation, you actually follow this way. You put 2 and 8 in the same column, and then you do the summation. 2 plus 8 equals to 10. But here, you write 0 here, and you write an increment on the top side of these two numbers, right? And you put the increment 1 here. So that's the result. Give you another example. How about 28 plus 44? When you do the summation, you actually follow this way. You first count what's the result of 8 plus 4, right? That equals to 12, and you have an increment for the previous digit. And here, when you do the summation for the second digit, you actually sum these 3 digits together, right? That is 1 plus 2 plus 6, 1 plus 2 plus 4. That equals to 7. So the result of 28 plus 44 equals to 72, right? For binary summations, you actually follow the same way. For instance, the simplest one is 0, 1 plus 0, 0. When you do the summation, that equals to 1 plus 0 is 1. 0 plus 0 is 0, right? And when you have, let me write it to here. Okay, I will erase that. When you do 1, 1 plus 0, 1, when you do this summation, the first digit, the first position is 1 plus 1. In binary numbers, the largest number or the largest value of a digit is 1. Just like in decimal numbers, the largest value of a digit is 9. Whenever you have a number, whenever you sum two numbers is larger than 9, then you have an increment, right? For binary numbers, it follows the same way. Whenever you have two numbers summed together, if the result is larger than 2, then you have an increment for the next digit, for the previous digit. So here we have 1 plus 1, the result is 2 in decimal numbers, but for binary numbers, the result should be 1, 0, right? So we have an increment for the previous digit. And then we sum these 3 digits together. That is 1 plus 1 plus 0. Here we have another increment, right? Because 1 plus 1 is larger, 2 is larger than 1. So the final result is 1, 0. Right? Alright, so that's how we handle the binary summations. I will talk more about binary summations in later class. But here you just need to remember when you have 1 plus 1, you have an increment on the previous digit. Okay. So here let me do the summation. Here we have 1 plus 1. The result is 1, 0, which means we have an increment for the previous digit. And here we have 1 plus 1 again. The result is 0, increment to the previous digit. 1 plus 0 is 1, increment is 0. So we have 1, 0 here. We don't have any more increments, right? So the result of summation is 1, 0, 1, 0, 0. And after you get the result of summation, you finish these 3 steps. So the final result of minus 12 is 1, 0, 1, 0, 0. Okay. So some people may get confused, and a commonly asked question is, when I have a binary number, how can I tell it's a signed or unsigned binary number, right? Because sometimes, just from the binary number, it's hard to tell. It's impossible to tell it's a binary number. It's an unsigned binary number or signed binary number. So here, if the question asks you to find the unsigned binary number, then which means the binary numbers in this question, they are they are signed binary numbers. So the question will provide you the additional information to tell you whether this number is a signed or unsigned. For instance, here, since we already know we are finding the binary representation of -12, so this must be signed binary number, which means the first digit 1 indicates the polarity of this signed binary number. Okay, then how we convert a negative, or how we convert signed binary numbers to signed decimal numbers, right? For instance, if I give you 0.0101, this signed binary number, how to find the decimal representation? The method is the same. We just need to decode this binary number, right? The method, in case you forget, the method we use to decode a binary number is we count positions, starting from right to left and starting from 0. So the position of these 4 digits are 0, 1, 2, 3. And then we can do the decoding. The first digit is 0 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0. That equals to 0 plus 4 plus 0 plus 1, which is 5, right? And since this is a signed binary number, so we have positive 5. And the first digit is 0, which means this is a positive decimal number, right? So it's positive 5. And we can verify that, right? Because we already find what's the value for positive 5, 0, 1, 0, 1. Then how to convert a negative binary number to decimal representation. For another instance, let's convert -12, this signed binary number, back to the decimal representation. So the binary representation of this, the signed binary representation of -12 is 10100, right? We also decode this binary number, and we count the position of these 5 digits starting from left to right, and starting from right to left, and starting from 0. So positions are 0, 1, 2, 3, 4, right? And here the difference with the normal unsigned binary number is here, since the first digit is 1, which means this is a negative binary number, right? So you have -1 in the first place times 2 to the power of 4 plus 0 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 0 times 2 to the power of 0, right? And then you do the summation. That equals to here we go. That equals to -1 times 16 plus 0 plus 4 plus 0 plus 0. And that equals to -12, right? So here you have to use -1 for the first digit, for the first one, because we have a signed binary number, and the first digit is 1, which means this is a negative binary number. Okay. Alright, so we have introduced, in today's class, we have introduced how to do the decimal fraction numbers to binary fraction numbers, and how to do the signed binary numbers with positive and negative representations. And we also introduced how to convert signed binary numbers to signed decimal numbers and how to convert it back, right? Here I want to give you some access problems. I want to give you some access problems. It's not the homework questions. Just the access problems. So the first one was the decimal representation of these signed binary numbers. Of this signed binary number, okay. And this signed binary number is 10110110. Find the decimal representation. I give you the result. The result is minus 74. Okay. And the second one is 01001010. What is the decimal representation? The result is positive 74. Okay. Don't copy the result. Cover the result first. Try to solve these two questions by yourself, and then verify your answers with the result, with the solutions. Okay. Second one. What is minus 128 in decimal I'm sorry. Yes, what's the minus 128 in the decimal representation? Okay. And what is the minus 23 in the decimal representation? Okay. Minus 28 give you the final result, that is 1000000. Okay. Minus 23 is 1001. Okay. All right. So that's all for today's class. And today is Friday. I will give you another assignment, which is the second exam. Exam 2. Okay. I will post exam 2 after today's class. And the due date for exam 2 is the next Monday, which is, let's see, what's the due date is April 6. Okay. And here again, as we mentioned, all exams are take home now. So, and if you have any questions, you can ask me through emails. Okay. All right. I'll see you guys next time.